A neříkal jsi, že mračna na Venuši jsou tvořeny z kyseliny?
Jo, říkal, a co?
Jak tam teda může cokoliv přežít?
Ty si neviděl tu novou přednášku od Januše. Tak se tady na to hezky podíváme.
Takže já všechny vítám na dalším zasedání Czech Society. Po letní pauze tu máme dneska nový talk a jelikož náš mluvčí je z jiného kraje, tak já přepnu spojitě do anglického jazyka. So welcome everybody to the meeting of the Czech Society. And it is my pleasure to introduce again Dr. Janusz Petkowski, who is professor at Wrocław University of Science and Technology. He's also one of the deputy PI of the Venus Life Finder missions, and maybe more importantly, also founding member of the Polish Astrobiological Society. And I think today we have a great treat. He will talk us about these missions to Venus, who I believe will be first private scientific missions to investigate possible life on different planets. So I am very eager to hear it, and I am also looking forward to the discussion afterwards. So please, Janusz, you can start.
Thank you very much. Thank you very much for this invitation. It is really a great pleasure to be here, at least online, and to share our work and our research with all of you. And also thank you for very kind introduction. And indeed, what we are going to talk about today is morning star missions to Venus, because our initiative, the Venus Life Finder, was sort of an initial concept study that we've developed, and now since then we've rebranded to Morning Star Missions to Venus. So that's what we do, and essentially I know that this is probably like more than 1 year, I guess, since my last lecture. There will be some overlap between the two lectures because obviously our work is sort of a continuum of what we do. But what essentially we will focus on today is our development of the private missions to Venus. And what we really would like to stress is that the Morning Star missions to Venus are all about the astrobiological the exploration of Venusian clouds. So we are not shying away from this, from astrobiology. We are not afraid to ask questions or to search for life in our own solar system, and we are not afraid to actually have a series of missions that have this astrobiology at the very center. And of course, you could ask yourself a question, is there any astrobiological value or potential for Venus? And this is essentially what we would have to start our lecture. This is sort of a general outline of what we are going to talk about today, because as you will see, everything actually is connected to each other, or all those points are actually connected to each other. The astrobiological potential of Venus is not something that people immediately actually, it's not something that comes to mind when you look at the planet Venus, of course, because it's so different than what we have here on Earth, or the environment that we have here on Earth is so different than the Venusian environment. But it's nevertheless, as I will try to convince you, is very much an astrobiologically relevant environment. Finally, this is something that hopefully will be also interesting to you, although I do not know how organic chemistry oriented you are. But nevertheless, this is also something that is extremely important when you develop the missions or formulate the science objectives for the missions, is the laboratory prep work ahead of the missions. And this is essentially something that we also do, and we specifically study something that nobody studies really in detail, which is the organic chemistry in concentrated sulfuric acid. And this is essentially, at the first glance, you might think that this doesn't really connect to the mission development, but as we will see, it very much does, because the understanding of the chemistry of sulfuric acid is directly related to the understanding of the cloud environment, sulfuric acid cloud environment on Venus as well. So as much as we understand this reactivity of sulfuric acid with various organics, then the better we would be able to actually formulate our science objectives for the missions. And finally, the second sort of half of my talk will be devoted to the missions themselves, which is basically first the rocket lab mission to Venus, which is actually quite advanced in its development, and hopefully the follow-up missions that we currently develop, which is under the sort of an umbrella term of Morningstar missions to Venus. So let's embark on this journey, and before we actually really dive deep into the clouds of Venus, we have to sort of remind ourselves once again what this object of our interest really is. And then essentially, Venus is often called the sister planet of Earth, and this is of course extremely misleading statement because it might actually be similar to Earth in certain respects, like mass and the overall radius, so the size. But the environment that we actually have there on this planet, on the surface, for example, is very, very different than what we have here on Earth. Specifically, the temperature at the surface is what? Approximately 467 or 65 Celsius degrees. So this is actually the hottest planet in our own solar system. The surface pressure is also approximately 90 times higher than what we have here on Earth, which is actually quite different as well. But where further differences also show themselves is in the atmosphere. So the atmosphere of Venus is mostly carbon dioxide and nitrogen, and what really makes Venus stand out is the presence of this is the so-called temperate cloud deck. And what I mean by temperate cloud deck is the fact that you have at the altitudes of, let's say, 48 to 60 kilometers above the surface, you have these clouds that actually have temperature range that is pretty mild. And that's why that's where the name comes from. And by mild, I mean that at the bottom of the cloud decks, you could expect approximately, let's say, 80 to 100 Celsius degrees. And at the top of the clouds, you could have, let's say, 0 to minus 20 Celsius degrees. So this is sort of a temperature range in which you could, in principle, expect, for example, complex organic chemistry to persist, not to mention, very hypothetically, life. But of course, the devil is almost always in the details because, as we briefly mentioned, the clouds of Venus are very different than the clouds that we have here on Earth. First of all, the clouds of Venus are made of a completely different substance. There is still liquid on Venus, but it is a very different liquid than we have here on Earth. The clouds of Venus are made of concentrated sulfuric acid, little droplets of concentrated sulfuric acid, as far as we, of course, understand this environment. They are also continuous and permanent, and what it actually means is that they are not like clouds on Earth, which can form and dissipate within, let's say, a couple of hours. They persist constantly on Venus, and they cover the entire planet. So this actually makes this environment a very stable environment. We are not actually changing these cloud decks very much over the time. So you see, you could look at this environment, at the concentrated sulfuric acid, at these very, very different conditions that we have there, and ask yourself a question whether there is actually any hint that there could be any biological activity in the clouds. And of course, this is a very important question because we are sending missions that are astrobiological at its core. So we actually should ask ourselves this question, whether there are any astrobiologically relevant observations made to date that could suggest that there is some sort of biological activity in the clouds. And of course, this is not a proof of life in the clouds, but nevertheless, this type of series of observations that have been done over the many decades now allow us to put forward this hypothesis about the potential biological activity in the clouds. And this is just a very brief overview, but what is quite important is that such anomalies that could be connected potentially, hypothetically, with biological activities, there is quite a lot of them. And one of the most important ones is the so-called unknown absorber. This is some substance that actually was detected or discovered almost 100 years ago. So soon we are going to have a 100-year anniversary of the detection of this phenomenon. And after 100 years of observations and research, we still don't know what this substance is. We only know that it is a very, very efficient absorber. It absorbs up to 50% of all sunlight that falls onto the planet. And basically, it is also a very dynamic phenomenon. It changes in space and time. It changes with it follows some sort of quasi-seasonal changes. And we have a hypothesis that it actually might be organic. And I know that you know that, and hopefully soon, because we are working on the revisions to the draft, we will be able to share some results or some hypotheses that indeed, who knows, maybe maybe the absorber is indeed an organic molecule and not just some random collection of organics, but actually a specific maybe even a specific class of molecules. This work is actually led by Dr. Janusz Petkowski, and hopefully we will be able to share this quite soon. Finally, we have the anomalies that are associated with the clouds particles themselves. And this is a debate about the results by the Pioneer Venus, obtained by Pioneer Venus like more than 40 years ago, which suggests that there is a third mode of particles in the clouds, and specifically that there are certain particles in the mid to lower cloud decks that are non-spherical and larger than the usual size of particles of few microns. This is a highly controversial discovery because there is now 40-year debate in the scientific literature whether this observation is actually correct or not. And some people think that these particles do not exist, and other people think that they actually do. So we don't know. 40 years of research, and we still do not have an answer. And finally, we can say that indeed the atmosphere of Venus is mostly composed of carbon dioxide and nitrogen, but there is a series of various different trace gases that have been detected in the clouds and that actually completely do not fit with the rest of the chemistry of the atmosphere. So we do not currently have the explanation for them. And the it was 5 years ago, but nevertheless, the very controversial discovery of phosphine is actually only the newest and the most recent of such gaseous anomalies. And we are actually, this is a coincidence, but it is actually almost exactly the 5-year anniversary of the phosphine discovery on Venus. And after 5 years of debates and research, we can say that this discovery is very much alive, and that there's a lively debate in the scientific discovery on whether phosphine is there, where it is in the atmosphere, and what it actually means. And now Professor Jane Greaves has new observations with the JCMT telescope, and hopefully she will also share these results and publish these results soon. But phosphine is, of course, not the only such weird gas in the atmosphere of Venus, because there is also potentially ammonia. Ammonia was discovered first by the Venera 8 probe, and as such, it was actually dismissed quite soon after the discovery because of the potential cross-reactivity with the chemical sensor that was used, and cross-reactivity with the sulfuric acid environment. But nevertheless, the ammonia came back to the forefront of the Venusian research in 2021, when Professor Rakesh Mogul actually embarked on the quest to reanalyze the data from Pioneer Venus, from mass spectrometer that traveled to Venus on Pioneer Venus probe, and then he found potential signals for ammonia in the data as well. This is, of course, not the proof of ammonia, but nevertheless, there is a hint that ammonia indeed is there in the clouds. And together with the nitrogen in the atmosphere, and as well as the nitrogen oxides in the atmosphere, they can together form the nice nitrogen cycle that is not unlike what nitrogen cycle that we have here on Earth. And this in itself actually could be a biosignature in its own right. And finally, we also have oxygen in the clouds. This is, again, a very controversial detection because we do not see this oxygen above the clouds. When we observe the Venus from the ground, we don't see it. but suddenly in the clouds, we actually were able to detect it, and it was detected by both Venera and Pioneer Venus probe. So this is a rare situation in which the Russians and the Americans actually agree on something, and they not only agree about the amounts of oxygen that were detected, which are small as compared to Earth, but nevertheless too large to be explained by by known chemistry of the Venusian clouds. But they also agree where exactly in the atmosphere this oxygen actually resides. So this is actually a detection that remains unresolved for now, again, approximately 40 years or so. And finally, we have other anomalous detections, like, for example, the high local abundance of water that maybe is correct, maybe not, and the unexplained profile of sulfur dioxide in the atmosphere. So there's nothing wrong, nothing really anomalous about the sulfur dioxide itself as a gas, because it's obviously produced by volcanoes, but the profile itself is actually quite peculiar. So as you can see, this is basically just my subjective selection of this of Venusian anomalies. As you can see, we have quite a significant list of such unexplained weird observations, and we have to know which ones of them are actually correct, which ones are errors of the measurements, and which actually could be attributed to some unusual planetary chemistry, and who knows, maybe even life. So this actually begs to have a mission, or again, Venusian missions that actually could revisit these measurements and these observations and see which ones of them actually will hold to scrutiny or the remeasurement with the 21st century technology. And finally, there is another aspect of Venusian clouds that is quite important to astrobiology, is the environment, the cloud environment itself. We actually try to convince everybody that that we shouldn't be afraid of sulfuric acid as a solvent for life. And at the first glance, you might think that this is a complete science fiction, because you can Google, what will happen to organic chemistry or various important biochemicals of our own life after addition or upon addition of concentrated sulfuric acid, and you will find, for example, spectacular YouTube videos that will show that if you add sulfuric acid, concentrated sulfuric acid to sugar, then you will vigorously have the vigorous, spectacular reaction that results in the formation of this sort of carbonaceous sludge blob that has nothing to do with complex organic chemistry, not to mention life. But of course, such spectacular YouTube videos are just a bit of a misleading view of organic chemistry in concentrated sulfuric acid, and they shouldn't be extrapolated to all organic chemistry. And this is essentially a wonderful work of Dr. Janusz Petkowski and Professor Stephen Benner. We now study organic chemistry in concentrated sulfuric acid for a couple of years now, and we can confidently say that complex organic chemistry can form in concentrated sulfuric acid, and even from very, very simple precursor molecules, like, for example, from formaldehyde or carbon monoxide. These formaldehyde and carbon monoxide could be or are essentially atmospheric gases. So you can, in principle, form this type of sort of carbon larger molecules, like polymers of sorts, in concentrated sulfuric acid in the clouds, and this is actually quite expected to happen. So existence of complex organic chemistry in concentrated sulfuric acid is a fact. It's just a question how different it is going to be from what we have here on Earth in our water environment. We asked ourselves a little bit of a different question. Which building blocks of our own biochemistry are actually completely destroyed or unstable or stable in concentrated sulfuric acid? And this is the wonderful work of Max Ziger from our team. He asked a very simple question: which amino acids, the building blocks of our proteins, are actually stable in concentrated sulfuric acid at concentrations that we actually expect to happen to have in the Venusian clouds, and also at temperatures around that in the Venusian clouds. And what he actually was able to show is that 19 out of 20 of amino acids that build our own proteins are actually stable in concentrated sulfuric acid for many, many months. So this is something that nobody actually studied this, so people assume that this is impossible and that these molecules will not be stable, that they will be immediately destroyed in this harsh environment. But this is not the case. The only amino acid that is really destroyed is tryptophan, while others sometimes undergo some chemical modifications like sulfonation or sulfation. But this doesn't mean that they are destroyed. They are modified in some specific manner. So this is a very simple experiment, but experiment that has actually profound implications for our missions as well. We now know that we should expect amino acids in the cloud environment because they are actually quite stable, and they could potentially be also delivered with meteoritic material. This was such a simple experiment, but yet the implications of that were so profound that we actually got even a cover of Astrobiology journal just by testing the stability of amino acids in concentrated sulfuric acid, sort of a 19th century style with, of course, a 21st century NMR spectroscopy, but nevertheless a relatively simple design of an experiment. So emboldened by this, we actually asked ourselves even more outrageous question: what is going to happen to the peptide bond in concentrated sulfuric acid? And I don't know if you are chemists, but in general, the peptide bond is probably some of the most important bond in our own biochemistry. This is the bond that actually brings together two amino acids in proteins. So this is a bond that allows us to build a large chains or large peptides and protein chains. So we actually can have this executive branch of our own biochemistry. And at the first glance, you would think that this is a completely ridiculous science fiction question, because obviously there is such a thing as acid-catalyzed hydrolysis of the peptide bond. So this bond should be chopped in acid completely, and nothing really interesting should be happening. But nevertheless, we were again very much amazed, because some of the peptides that we actually tested are completely stable in concentrated sulfuric acid. And we have some dedicated papers to explain why it is so. I cannot go to details about this as well, but nevertheless, this gives us an opportunity to actually study a formation of large peptides and stability of large peptides and proteins in this concentrated sulfuric acid environment, because it doesn't mean that all of them are actually going to be destroyed. There are going to be some arrangements of amino acids in peptides that are going to be actually completely stable. So at the same time, in parallel, we also asked ourselves a question about another aspect of our own biochemistry, which is our genetic component. So all the famous letters of our genetic code, like for example, guanine, cytosine, adenine, and thymine, are they stable in concentrated sulfuric acid? And yes, they are so stable, in fact, that the NMR spectra do not really change after 1 year of incubation in concentrated sulfuric acid at all. Like, they do not change at all. We actually get bored and didn't measure past 1 year. It doesn't mean that, after 1 year they fall apart. It means that we didn't measure longer than. Yes? So they probably can stay there for many, many years without any detrimental changes, like in water, basically. And of course, there is another question related to that. Can you actually bring them together and form a polymer? Form some sort of genetic-like polymer that could function in concentrated sulfuric acid? And we have to remind ourselves that yes, indeed, the YouTube videos are correct. Yes, the DNA will not be stable because it contains ribose, deoxyribose sugars with the phosphate backbone, and this backbone and the deoxyribose will be completely chopped to pieces in concentrated sulfuric acid. But it doesn't mean that you cannot have something else. If you substitute this ribose and phosphate backbone to some other backbone, like for example in peptide nucleic acid, you are going to have this polymer stable in concentrated sulfuric acid at room temperature for quite a long time. Unfortunately, we tested this and it's not stable above 50 degrees. So we are not exactly there yet. But what is actually quite encouraging is that it falls apart in concentrated sulfuric acid in a very specific manner. So it doesn't decompose completely to an amorphous goo. There is one single bond here marked in red that actually breaks and eventually leads to the destruction of the entire polymer. But if one bond breaks, then we now actually can work, and we work on that quite intensively, how to actually substitute this so we can stabilize this for high temperatures. Because we would like to actually have this polymer stable at 100 degrees in concentrated sulfuric acid as well. So we are not exactly there yet, but we are slowly getting there. And finally, we have another aspect of our own biochemistry. What about the cell-like structures? What about the membranes? What about the actual cell-like barriers, the cell walls, cell membrane, something that denotes the inside of the cell from the outside environment? This is an important aspect of biochemistry, no matter its chemical makeup. And we forged a very nice collaboration with Dr. Daniel Duzdevich, Colin Nisler, from Professor Jack Shostak lab. And we were able to show that indeed such membranes, micelles, and vesicles do form spontaneously in concentrated sulfuric acid. And I could bore you with all kinds of biophysical analysis of various graphs and curves and so on, but seeing is believing, as they say. So this is a wonderful picture from the fluorescent microscope that shows that formation of such vesicles. And as you can see, they are pretty diverse in size and shapes. And what is actually quite important is also they actually seem to have a complex dynamic behavior. Sometimes they actually form these sort of large tubes, and they bud smaller membrane structures and smaller vesicles, and they do this actually entirely spontaneously. So this is quite important because in water, for such behavior, this sort of purling behavior, as biochemists call it, for the purling behavior to happen in water, you need special conditions like turbulent water flow or special lipid composition of the vesicle. In sulfuric acid, we've seen this spontaneously without any special preparation. So either we were extremely lucky and by accident we actually chose the lipids for these experiments that automatically allow for this behavior, or maybe there is something special about sulfuric acid that actually allows this type of dynamic membrane behavior. So where does it all brings us? It has some important implications in general, but one of these important implications is that we actually try to formulate a new paradigm for sulfuric acid as a solvent for life. So we are not afraid of that. We think that water is not the only solvent for life that is possible. Life needs some sort of liquid to exist in and some temperature range that will allow the formation and persistence of complex organics. But this liquid can be something else. It might be actually sulfuric acid, and sulfuric acid does not look that bad. It actually, thanks to Jan Spacek and Steven Benner, we know that the complex organic chemistry actually can happen. And what is more importantly, it can form from very, very simple precursors, even gaseous precursors like carbon monoxide. We can build the complex polymers, and we are working on that right now. We still don't know if these bases will pair in concentrated sulfuric acid because of the protonations of the bases. But hey, baby steps, yes? We started a couple of years ago and nobody asked this before, so we have to give ourselves some time to answer all of those questions. But nevertheless, such polymers we can now actually make. We can also stabilize the peptides, yes? I didn't go into details here because this is a hard organic chemistry, but nevertheless we can stabilize the peptides, and who knows, maybe we can actually make them fold and have catalytic activity. This is some sort of work for the future. All of that in concentrated sulfuric acid. And finally, thanks to our collaboration with Professor Jack Shostak and Daniel Duzdevich and Colin Nisler and others, we actually were able to show that the membrane formation and vesicles form exactly, well, as easily as in water, if not even easier. Yes, and they exhibit a very, very complex behavior. So that's the first reason why. The second reason why, if we didn't do these preparatory experiments, we would really not have the full scope of what we could actually expect if we actually worked and designed our space missions. So now we know that if we actually travel to the clouds of Venus, we can ask very, very specific, we can constrain our scientific questions, and we can boldly ask the questions about the organic chemistry in the clouds, because we actually should expect this type of chemistry there. And the Rocket Lab mission is the first step on this, in this endeavor. It might be a small mission that actually, has very short duration, because we are going to just basically drop a probe into the clouds, which will reside there only 4 minutes or so, or 5 minutes. But this is enough for us to ask and answer, hopefully, a very bold question, which is whether there is organic chemistry in the clouds of Venus. Nobody before, no mission before, and there were many, many of them, ever asked this question. So we are going to be the first to actually ask about organic chemistry in the clouds, and we have a fantastic instrument to do that. And this is basically an instrument called autofluorescent nephelometer, AFN for short. And this is an instrument that is developed by Darrell Baumgartner from Droplet Measurement Technologies Company and Cloud Measurement Solutions in the USA, and of course his team of engineers. And what this instrument is actually going to do is essentially twofold. First, we would like to characterize the clouds of Venus. Yes, we would like to characterize these particles there, like, for example, see their shapes and sizes, especially also the size and shape. If you remember from a couple of slides back, we had the table of various different anomalies, and one of the anomalies is the weird Pioneer Venus measurement that suggests that the sum of the particles are actually non-spherical. We hope to actually resolve this phenomenon, or this anomaly, and see if we indeed see some non-spherical particles in the clouds, which would suggest that not all of the cloud particles are actually made of liquid concentrated sulfuric acid. And finally, the AFN actually has, so apart from the fact that we have this so-called polarization detection model that will allow us to characterize the properties of the particles, like size and shape and so on, and also measure refractive index, which is sort of a proxy for chemical composition, we also have a unique feature of the AFN, which is the fluorescence detection module. So when we shine a laser on a particle, and we can do this particle by particle, so AFN is an instrument that can actually probe each individual particles in a particle and particle mode, which actually gives us a very potentially very powerful information. But what is quite important is that we can actually shine a laser on a particle, excite whatever is inside of it, and then if it actually fluoresces, we will be able to detect this fluorescence from the particle, because we have the dedicated fluorescence detection model. And why it is actually so important? Because the fluorescence actually can be used as a proxy for detection of organic chemistry, of organics. So it is a way to detect, but of course not identify, organics inside of the cloud droplets on Venus. Of course, we will not be able to distinguish what these organics are. So if there is some sort of boring benzene dissolved in the cloud particle, it will give us sort of the same fluorescence signal as something very complicated, like for example, our genetic polymer, so to speak. But nevertheless, this is the first step. We have to start somewhere, and we are aiming for detection of organic molecules. And this is a wonderful work. A lot of preparatory work actually was required before I could condense into this one slide. But it is important to mention that the selection of the specific wavelength for the AFN laser was actually motivated by a lot of hard work by Dr. Janusz Petkowski and Professor Stephen Benner. So the laboratory preparatory work is actually key for the development of the missions. And finally, when it comes to the probe itself, the probe itself is actually very small. It's approximately 40 centimeters in diameter. The positioning of the AFN, a lot of work and modeling and tests actually went into the positioning of the AFN in the pressure vessel. What is quite important is that we actually probe the droplets approximately 20 centimeters from the capsule skin. And why it is that is because the Rocket Lab mission is actually pretty simple. It's design. We do not detach the heat shield from the probe. We don't have a parachute or anything of that sort. We just so basically the heat shield could in principle create this sort of ablation products that could be detected by the AFN. We positioned the AFN in a way that to avoid such detections. And also there is a lot of work on laboratory that we actually perform to rule out the potential false positives from the AFN of this sort. So the development of the rocket mission the Rocket Lab mission actually goes pretty smoothly. We have now completed the flight instrument. The AFN is ready. We had our first integration tests with the probe that is going to be actually dropped into the clouds of Venus. And thanks to our wonderful partners and collaborators at NASA, they were also able to apply the heat shield of the heat shield material onto the probe itself. And as I mentioned, in a summary, we can say that yes, the mission itself is actually very simple. It's in terms of its design, but the probe itself is going to pierce or travel in the clouds for only 5 minutes or so. But it is enough to turn on the AFN, to probe the particles with the AFN's laser, and then basically send the signal back to Earth. And we hope that this mission, the Rocket Lab mission to Venus, is going to be a wonderful start for a series of missions that are going to follow. And this is basically missions that the Morningstar that are going to be developed under the umbrella term Morningstar missions to Venus. And specifically, we have a series of sort of habitability missions that are focusing specifically on astrobiological questions, as I mentioned. So specifically, we would like to build on the Rocket Lab mission detections of organics, if we detect them, and this time identify or aim for identification of complex organic molecules that could indicate the presence of life. So we are not only detecting, we are now hope to actually find out what we have detected. And then obviously from the table from a couple of slides ago, we had a series of these unknown or unexplained various gases and various anomalies in the clouds. We would like to tackle them. We would like to, for example, also aim for detection of the reduced and anomalous molecules that could be the signs of disequilibrium chemistry, and at the same time that could actually have the potential to be biosignatures in their own right. And finally, we really would like to study the environment, the cloud environment itself. It is hard to imagine, but the acidity of the cloud droplets was never measured directly. It was always inferred from other measurements or modeled from various various atmospheric models of the Venusian clouds. We would like to measure the acidity of the cloud droplets directly, so actually see how much acid you have there. This automatically informs what type of chemistry we should expect. The diluted acid, for example, is a very different substance, chemically speaking, from a concentrated sulfuric acid. So we would like to confirm that. And finally, we would like to also characterize the cloud particles themselves, see if they are liquid, solid, both, if they are homogeneous, not homogeneous. Should we actually expect all of the particles to be the same? Or maybe they actually have populations of some sort that nobody before expected. So we have series of concepts of missions that we are now working on, and this involves both the concepts that are sort of using a parachute, as well as more scientifically sophisticated concepts that actually are utilizing balloons. And the parachute mission is essentially sort of a natural extension of the Rocket Lab mission to Venus, because it's essentially attaching a parachute to a probe, to a probe that is going to pierce the clouds of Venus, is essentially giving us additional time in the clouds and extends the duration of the mission to, from 5 minutes, like it is in the Rocket Lab case, to, 1 hour of the duration of the sort of science operations within the clouds. And we are still, this is sort of an overview of the probe, but of course, this is something that we still work on. We are considering some of the instruments for this type of concept missions, but this doesn't necessarily mean that these particular instruments are going to be the final ones. This is just an overview. For example, we are considering a very, very nice instrument that is called a mini tunable laser spectrometer. So that's a so-called mini TLS. And this is a spectrometer that is able to detect these trace gases in the atmosphere, these anomalies. We can tune it to specifically to detect, for example, phosphine, ammonia, or other reduced gases in the atmosphere that lingered as such anomalies for decades. And finally, we have also a very novel instruments, like, for example, the top acidity sensor that is being currently developed by my colleague, my friend, Professor Mikkel Pajusalu at Tartu Observatory in Estonia. So this is a single particle, a single chemical. It's essentially a chemical sensor, but it is a single particle acidity sensor. And in this case, we actually will be able to get maybe a profile of acidity in the clouds and see how acidic these clouds really are. When it comes to the balloon mission, on the other hand, we can ask we can sort of use the very sophisticated scientific instrumentation and ask much more complicated scientific questions. In this case, the duration of the mission is going to be much longer. We are going to stay in the clouds for, let's say, approximately 7 days or so. So this allows us to actually do much more sophisticated scientific experiments. We are going to fly a balloon at around, let's say, 50 kilometers, 52 kilometers in the clouds. This is at the level where there is this sort of boundary between mid to low clouds. The concentrations of sulfuric acid is expected to be quite high, and at the same time, this is also a level at which these mode 3 particles should be present. These non-spherical particles allegedly discovered by the pioneer Venus. So we are at the sweet spot of the Venusian anomalies as well. And for this mission, we actually consider a very, very well designed mass spectrometer. This is called an origin laser desorption mass spectrometer. We have a wonderful collaboration with Professor Peter Wurz and Dr. Andreas Riedel from the University in Bern in Switzerland. And this instrument is actually built for space. Yes, so we now hope to modify with our collaborators. We hope to modify this instrument to adapt it for our Venusian balloon activities. This, of course, means that a lot of work is going to, and we are working at it at these aspects currently, that a lot of engineering work has to be done, because you cannot just put there the mass spectrometer on its own, because obviously you cannot just feed the sulfuric acid droplets to it and in hopes of actually analyzing the chemistry, you would destroy the intricate machinery of the spectrometer itself with concentrated sulfuric acid. So we have a lot of additional machinery, for example, and we test that is aimed at removal of the excess sulfuric acid before we actually feed the collected material to the spectrometer. And one of such additional instruments is, for example, first of all, sample collector. This is something that is developed and tested currently by Dr. Jarosław Jakubiewski from MIT, and he's sort of designing this and building this fog harp-like instrument that is going to collect the droplets and essentially feed them to the sample reservoir, which in turn is going to present it to the special sample handling unit. And what the sample handling unit is essentially it's a way of evaporating excess sulfuric acid under low pressure, so we can remove the sulfuric acid before we actually feed the material to the spectrometer. And what we hope to achieve is that hopefully in these sulfuric acid droplets that we collect, we are going to have residual organic material that will be able to be detected by this instrument, by the Origins mass spectrometer. So there is a lot of work ahead of us on this, both engineering as well as scientific, because we also have to test how this scientifically, what to expect, what organic chemistry we should, for example, expect, and so on, so on. But nevertheless, we also develop some other potential instrumentation for the balloon mission and other types of missions as well, which are the so-called mini probes. Why not actually have a lot of sensors or various different sort of sycamore-like instruments or probes that are going to be spread all over the place in the clouds of Venus, and sort of give us an altitude profile of of, for example, gases compositions or acidity, because on this type of level probes, we can have all kinds of different sensors. Like, for example, we can detect specific gases. We also think about designing an acidity sensor that will be compatible with with this type of design. This is an engineering work of the British company Space AM and Chris Isaacs and Nick Jones in particular. So this is something that we also work on together with them as well. And finally, we work on the potential for atmospheric sample return. This is an extremely futuristic concept because it borderlines on science fiction, and the reason is very simple. I mean, a lot of technologies that we would need to finalize such a mission actually do not exist or are so underdeveloped that we do not even know if they will work. But nevertheless, it is important to a certain degree, also entertain the idea of atmospheric sample return for one very simple reason. If astrobiology and life detection is at the center of our activities, then if we are to get any proof of life in the clouds of Venus, then we have to collect the sample and bring it back to Earth so we can analyze this in Earth laboratory. Otherwise, we are always going to have, we have essentially with our own Earth laboratories, we have many more analytical chemical techniques that we could apply for life detection directly on these samples. So we are also entertaining this possibility of atmospheric sample return, but of course it is a very difficult task. Like, for example, working on a concept of launching a rocket from a balloon, it's not something that is essentially engineeringly easy, especially if it is done on another planet. Yes. So yeah, I guess I will finish here, and I will just summarize by reminding everybody that we hope, we are actually, we have this astrobiology at the very center. So so the Morningstar missions to Venus are astrobiology focused missions, and they also operate under this quite novel approach of private-public partnership. We are not afraid of these very controversial questions or topics. We actually hope to find signs of life elsewhere in the clouds of Venus, and to study these clouds in detail, specifically focusing on the organic chemistry. This is something of an overarching theme of our work. And of course, I will end by acknowledgements and thanks. Nothing that I told you and shared with you today wouldn't be possible without the wonderful team of people that are developing these missions with us, and specifically without Professor Sarah Ziegler. Professor Sarah Ziegler is a leader of our entire initiative, and every research and every approach that I've discussed with you today is actually thanks to her and her leadership. We also have, of course, an involvement of the rest of the Morningstar core team. Our mission director, Dr. Jared Atkinson, joined us recently, and he's doing a tremendous work, as well as the rest of the core team of engineers, Weston, Rachna, and Dr. Christopher Carr, as well as Yaro. They are just absolutely stellar at their job. And of course, there is a lot of other people who are involved as well. And this is not only an academic setting, but it's also a private sector. So many different companies are also involved in our activities. And of course, a special thanks to Rocket Lab Venus team and the collaboration that we have with them. It is really a privilege to be part of this. And finally, I have to, of course, also thank our organic chemistry team. Without them, we wouldn't be able to constrain our science objectives for the mission. So this is not some additional side project. It's actually an integral part of the mission development. So thanks to Max Ziegler, William Baines, our NMR expert, John Grimes, as well as Daniel Duzdevich and Colin Isler from Professor Jack Shostak Lab, as well as, of course, Jan Spacek and Professor Steven Penner. Thank you very much, and I welcome any kind of questions.
Okay, thank you. It was really great talk. So I hope there are many questions.
Thank you.
So, okay, so I have a question about this balloon mission because I am a fan of balloons. So I wanted to ask first, I presume your filling gas will be helium.
Yes.
And, of course, and how you stabilize the balloon in one height? Is a pressure stabilization or something else?
So you see, that's a very good question. So yes, the balloon is going to be stabilized. We are specifically, so this is not going to be a variable altitude balloon. Yeah, so it's going to be, we specifically chose our favorite altitude, which is this 52 kilometers. Again, this is because of the science reasons and that this is sort of a sweet spot for various peculiar particles and can potentially chemical composition of the clouds and so on. How do we stabilize the balloon? Well, this is a balloon engineering question, which actually should be directed um, um, to Mr. Dr. De Jong from a Thin Red Line company. Because Maxim De Jong is actually our balloon expert, and he has a dedicated company on this. And to be honest, I do not know how he does this. Yes, and it's basic, but yes, absolutely, we know this. I mean, this is his forte, and he basically knows everything about ballooning. Yes, so he's a true expert on this. It's really a wonderful also privilege to work with him on this because we really have a top-notch. Balloon solutions essentially, if I can use this term. Absolutely, but apologies, I cannot answer these balloon the questions in detail because I wouldn't want to actually mislead you also on the engineering aspect of this development.
Okay, no problem. Well, I imagine one way how to stabilize such a balloon would be to have the envelope so strong, so you just pressurize the inside, and if you have strong envelope that doesn't burst, this will stabilize in such a level, maybe like that. So additional question, I also imagine myself already living on Venus, on the clouds, in some floating cities, and so how would you guard you against this sulfuric acid? What material you should wear? Or how do you probe guard against this sulfuric acid and stuff like that?
So this is an interesting question, actually, because there are many chemicals or polymers, for example, that are completely resistant to concentrated sulfuric acid. Yes. Or resistant enough that we can actually use them for the duration of the mission, even if we consider a long-term mission like a couple of day balloon mission in the clouds. One of such acid-resistant substances is Teflon. Yes, Teflon-covered balloons or Teflon-covered instrumentation is something that is actually that is actually a pretty attractive solution. And this is probably something that we will also use. So that is, and there are many more polymers of that sort. I had a list in one of our papers. We actually have a list of that. I don't remember every position from this list, but in reality, I would say, is that finding such sulfuric acid resistant polymers is not such a difficult task because we actually have quite a bit of possibilities here.
So hello, I'm Lukáš, and nice talk. And I want to ask a question related to the balloon mission. Whether anybody has done any calculation about the delta V of the rocket, that would be.
Oh yes, we have all of that. So we have all the calculations. This was wonderful work of Rachna and Weston. Again, I will not actually I will not give you an answer to this, because this also changes quite a bit with respect to what do we actually say or send. So I think that we have all of this information in our final report, but I will not. I will probably refrain from giving you an actual values here.
I would like to ask, you are searching the organic compounds there. So what you personally or your team expect, how complex life can be in a certain altitude, say in the 50-kilometer altitude, what kind of life we can expect there, or you would like to see there? Only the compounds or something more complex?
Yeah, this is a very, very interesting question, actually, because there are two aspects to it. So we technically would like to look for signs of life, of course, but uh, there is a very interesting question about how much we can actually pack inside of a cloud droplet. Yes? So we can approach this from that point of view. Let's say that the cloud droplets are few microns across, yes, in diameter. Do we expect these cells, let's say that we have a cellular life of some sort, to reside in the cloud droplets, in the sulfuric acid? Then obviously they cannot be larger than the size of the droplet. On the other hand, we could, in principle, envision, because sulfuric acid is not a volatile solvent, it will not evaporate in the atmosphere at the temperatures that the clouds are. We could, in principle, envision that this life floats independently of the droplets itself, or of the droplets themselves. Still microbial, of course, but it might not be actually limited by the droplet itself. This is also a possibility. Now, it would have to be based on sulfuric acid, of course, because if we had some life that is based on water, then of course it would lose water to the environment. But now there is another point to this also. There might be a situation that we have complex chemistry there. We even might detect it with the origin mass spectrometer or some other instrumentation that we eventually are going to choose, and that it will not be life. Yes. What if we actually have some sort of weird or complex organic chemistry that doesn't have a characteristics of life as we know it? I don't know. I mean, what we really hope to detect first, so baby steps, we essentially would like to apply this sort of baby step approach, is that we first ask a question about any organics, and then we modify our understanding of this environment as we actually gather data. But yeah, this is a very good question. I mean, I don't expect multicellular complex life. Yes, I expect some sort of microbial life at best. And who knows? And this is the other thing that I think that I once had a discussion with Janusz Petkowski about this. In principle, you could imagine that life could inhabit a droplet and treat this droplet as its sort of quasi cell. Yes, because it is sort of its own micro universe. Yes, which has a very clear boundaries. Yes, it's just a droplet. It will not evaporate, and it could, in principle, be treated as a sort of its own mini cell to a degree. So yeah, and maybe there's some complex chemistry going on there that doesn't really have the classical cellular structure. This is what I wanted. This is what I actually wanted to arrive at. So yeah, we don't know, but this will not be a very complex life if it exists there at all.
Okay. Maybe follow-up question. I just thinking out loud here. If the droplets in the clouds can communicate with each other, like they smash into each other and they separate and stuff like that. So
This is a fantastic question, because this is something that this is actually a tough one for life, maybe. Although we can quote Jurassic Park, Dr. Ian Malcolm, and say life finds a way. Yes, obviously. That's actually a very nice quote. I love it. Now, why this is an important question? Because for such small droplets and of small of droplets that are made from from a substance that has such a high viscosity like sulfuric acid, the fragmentation of droplets is essentially not happening. Yes. So what happens is that the droplets can merge with each other when they, let's say, heat or when they actually meet each other in the clouds, but they will not fragment. They will not break. They will not sort of divide into smaller ones. So it's not going to be like for example, when a nice rain droplet falls and it fragments into there is entire physics around it, and there is a mysterious so-called Weber number that actually has denotes the boundary between when the droplet actually can fragment and when it cannot. And sulfuric acid droplets, when they are so small, they will not fragment. Now the question is, does it mean that life would not be able to divide or wouldn't be able to travel between one droplet or another? Does it mean that that this life would be somehow stuck in one drop? I have no idea. We have this a dedicated paper with a complicated so-called life cycle, of course, a very hypothetical one. I have to be really clear about that so people do not quote me that this is something that is proven. But the point is that in principle you could have a life cycle even with the deposition of the biological material under the clouds and so on, very complicated sort of cycle in which you do not need to drop the droplets to be actually fragmenting. And we assume only a passive fragmentation because we obviously can imagine, although very hypothetically again, that the microbial life itself somehow manages to force the fragmentation of the droplet. Yes, that in principle could be happening. Of course, this would need a sophisticated molecular machinery to do so, but it will not be unlike, let's say, for example, a cell division, but just done on the droplet. Yes. Now, again, we can quote Ian Malcolm and say life will find a way. If life exists in the clouds of Venus, then this ecological problem would have to be solved somehow. Yes. And also, there is another, if I may do the follow-up to my own statement, or if I may ask myself a question, there is obviously another issue, is that if you look at our own clouds, then they are full of life. Yes, there's a lot of bacteria in our own life, in our own clouds, that travel across the entire globe. And there are even specialized predators in the micro sense, of course, like the pathogenic bacteria, like Pseudomonas syringae, for example, that is actually attacking crops, travels from one continent to another in the clouds and attacks the crops, is deposited with rain onto the crops and essentially attacks these crops. But it is always, even if this our own bacteria in our own clouds, they always have in their life cycle the deposition on the surface of the earth. Yes, this is where they want to be. Even if Pseudomonas syringae, for example, has a special enzyme in their own membrane that actually catalyzes the formation of ice. This is quite amazing. That's why I say that Ian Malcolm is probably correct, because life will find a way. If you have an enzyme and a protein that can catalyze the formation of ice, and as you travel in the clouds, you form an ice shell around to protect from UV, from whatever it is, from whatever elements, then maybe you can actually do everything. Yes, but at the same time, of course, our own cloud life always wants to be deposited on the surface. We still don't know, after decades of research of our own cloud biosphere, we still don't know if our own microbial life can actively divide in the clouds. We know that they are metabolically active, that they do a lot of things in the cloud droplets, that they even produce like a membrane around individual cloud droplets. This is also happening. So they sort of hijack the droplets themselves also for their own purposes. This all happens. But the funny thing is that we still don't know if they divide in the cloud droplets in the atmosphere. We don't have that data. If they don't, then maybe this is an impossibility. But on the other hand, we know that the Earth's surface is habitable. Earth is a planet that has everything, that the entire planet is habitable, not only surface, subsurface, the atmosphere, everything. On Venus, you have a different case. And this is a rather lengthy and rambling answer to my own question. I finally arrive at it, is that you have to have a mechanism in which you stay in the clouds indefinitely. Because you are constantly fighting against the gravity, obviously, and even a small particle is going to have to fight with gravity. So how do you solve that issue? Of course, this is probably not that difficult. I mean, there are various different possibilities that you could achieve that, but nevertheless, you have to achieve something that we do not have on Earth, which is the entirely and strictly aerial biosphere. That's it.
So if I understood correctly, two droplets, when they collide, they always like merge and create bigger droplet, or?
Yes.
Okay, so
Yes.
if life is created in one droplet, is there any way how it can spread to other droplets?
Thank you very much. This is the question. And we had a paper when we actually tried to solve this problem in a passive way, knowing that the magical Weber number doesn't allow for the sulfuric acid to fragment, as far as we understand this, of course. And we had this, idea that if the droplets are being deposited eventually with the gravity, they are deposited below the clouds. When it is hot there, but not too super hot. Then the droplets can actually the sulfuric acid can dissipate, and it's essentially the whatever the content is inside can be drafted back up, because there are sort of vertical air movements also in the atmosphere of Venus, yes? So there is an idea of that sort, that we specifically wanted to have an idea that will be passive, yes? Because we can obviously come up like Ian Malcolm style and Jurassic Park style with all kinds of active mechanisms when life can actually do that. And who knows, maybe this is exactly what life does, the active spreading from one droplet to another. We could imagine, for example, a microbial life, and completely hypothetically imagining at this point, that you have sort of you can propagate sort of a spore outside of the droplet, and then you can shoot the spore out of the droplet and hope to hit another one. That is an active mechanism that allows you to spread from one droplet to another. But of course, active mechanisms involve an actual evolution of certain behavior. Now, the passive ones, it looks like the droplets will not be able to fragment. So you have to actually deposit yourself. You have to leave the droplet in some other way, and you effectively have to destroy the droplet underneath of the clouds. So you can then hope to be lifted up by the air movement back into the clouds, where the contents of the droplets, like for example some spores, could attract and act as a cloud condensation nuclei and then essentially close the cycle again. So we have an idea of that sort, of course, but the lack of fragmentation of droplets is actually an issue. That's for sure. Just staying in the clouds indefinitely is an issue. We had series of papers on these topics, and it's a quite long and complicated thing I could just prepare another lecture on that topic, But yeah, absolutely, great questions and great points.
Okay, I saw on one of your slides that the Rocket Lab mission is scheduled for 2026, but is there any precise date for the launch?
No, we don't have a we hope. Of course, I'm not a spokesman for the Rocket Lab, but at this point we can say that we, for example, have an opening window for summer 2026. By whether this 2026 date is going to be the launch date. Currently, yes, we can say 2026. One possibility is 2026, but of course we have to be aware of one thing, that this type of activities is not a sprint. We don't have to be absolutely married to one particular date. If there is going to be another date for launch, this is not going to be anything bad. Yes, because what we really want to have is that this mission is successful, and not that this is or any mission for that matter is successful, and not that they are actually rushed in any way.
Right. So whatever that date will be, I think it will be very nail-biting occasion.
Oh, I hope so. Yes.
But
yeah.
I think I speak for everybody that we will wish all success to that mission. And regarding that, do you also think about possible launch vehicle for the morning start missions, which are much more heavier? So I guess the Electron
Yes,
is out of the way for that.
absolutely. I mean, we have multiple options, and well, I mean, of course, we are building a partnership with Rocket Lab, of course, with our first mission. So hopefully we will be able to continue. But of course, we are considering various different options, and a lot of possibilities are on the table in this case. Absolutely, a lot, quite a few. But I will not actually say anything concrete on that at this point, at this stage.
Okay. I have a comment actually, because I think what you're doing is not only great but also important, because these private public missions for searching life, I think they could, if successful, and I think they will be successful, they could galvanize like other private and public bodies like universities and institutes to they will see that it's possible and it's in fact cheap. They're not so complicated to send missions to other bodies, and look for like everywhere in the solar system. And one thing I think it's important in my understanding, that you actually have like some idea what this life on Venus, if it's indeed there, should look like, given the problems it has to solve, and also this quite interesting work about the organic chemistry in the sulfuric acids, which I was quite unaware of. It's kind of very interesting results. And if you compare that with, for example, the Viking missions, which look for life on the Mars, but they didn't really know like what to look for exactly. So they look for general, let's say, metabolism or some aspects of metabolism on Mars. And I think the one reason of that those missions are not considered successful is because there wasn't like clear idea what the Mars life should look like. And Venus, in that sense, it gives you much more precise idea. So I think many of these anomalies and stuff like that will be hopefully resolved in your missions, and you have like very interesting ideas about this life, and you test it by this battery of missions. I think this is exactly the correct way how to do this. So and given
so.
that,
Thank you.
I think it will be we will be entering maybe new stage for astrobiology. And in that sense, I hope you best of luck in continuing this work.
Thank you very much. I mean, this is very kind of you, and I hope that this is also not the last time that I can share with you our progress. Because as I mentioned, I mean, we constantly work on it, and the engineering solutions, the concepts, actually they evolve over time. So hopefully I will be able to share more informations in the future, and maybe some improvements to the current solutions that we consider. And I think that you are completely right. Imagine that we didn't actually study the organic chemistry in the clouds of in concentrated sulfuric acid. Yes, we would, let's say, have this mindset that everybody had or everybody has, hopefully not for long, that this concentrated sulfuric acid cannot actually sustain any organic chemistry. Yes, there are these papers in the scientific literature that have uninhabitable Venusian clouds are uninhabitable in the title of the paper. And why they have it there is because they look at this from the point of view of the abundance of water. That's obvious that they are uninhabitable from the point of, of course, we can imagine even life that is working that is actually functioning based on water, let's say, even in that environment. But again, it is a bit of a stretch, and definitely this is going to be a life that is unlike any life on Earth. But to study this basic organic chemistry, this is what Janusz Petkowski and actually Stephen Benner constantly say, that unfortunately, different sciences do not talk to each other. And that is a problem. That was also a problem with Viking missions, yes? That you had organic chemists that didn't talk, that weren't probably, I don't know, I do not want to misinterpret anybody's work, but there was not so much organic chemistry in the Viking in the preparation of Viking missions. Yes, so the problem with such complex topics and developments is that you have to bring all of these sciences together. Without that, you can actually look for something that will never be there, or you can misinterpret your environment or what you should expect so much that your science goals would never align with the reality of the situation. Yes? And it doesn't, like, I still think, and this is my personal subjective opinion, I still think that there is something alive on Mars. I still think that there is. And, and I actually think that our solar system is actually full of life of all kinds. Yes. But we constantly, and this is great that I can actually have a little bit of a mini rant at the end of our meeting. But we have to fight with terracentric views about life. Our life that we have here, with all of its biochemical solutions, is a consequence of our environment that we have, and not a template for everything elsewhere out there. Because if we go to Mars, we are going to have Martian life there with its own specific biochemical adaptations to this environment. And not just suddenly some microbes from Earth. Like, probably not, because this Martian environment, even if that at the first glance is quite similar to some Antarctic desert, it's not exactly Earth. And not to mention Venusian clouds. They are so different that you cannot expect any solutions that we have here on Earth to be actually transferable to the clouds of Venus. So this doesn't mean that the clouds of Venus are inherently uninhabitable. It means that they are uninhabitable for Earth life. But at the same time, we can say that the bottom of an ocean is uninhabitable for elephants. Yes, because elephants actually adapted to a completely different environment, not the bottom of an ocean. So that's my problem. This is the entire problem of the astrobiology community. I think actually one of the serious one. When you look for life elsewhere, you should look for life and biosignatures and everything of that sort in the strict context of the planetary environment that you have. And not through the lens, not to drag your own sort of view of Serengeti, back to Mars and see if the Serengeti plains somehow overlap with Mars, because obviously they don't, but it doesn't mean that there is no life on Mars. Sorry, that was my mini rant at the end.
No, it's perfect. I also wanted to say I was very happy to see that slide about the sample return from the Venus cloud. Of course, this could be technically very difficult, but I think sample returns are very crucial for this to really know what we want to know. And if you manage to actually pull off this sample mission from Venus, it would show like NASA, how it's done, and that we can do it.
You know what's the problem? And this applies to everything, to even to Martian sample return, to any sample return. Like the collection of the sample itself, and with Venusian atmospheric sample return is actually an even more serious problem. The collection of the sample itself can potentially destroy your material inside. Because imagine that, and this was actually one of the questions that one of the sort of science goals that we had for the Morningstar missions, is that we want to see if the cloud droplets are actually homogeneous. Because everybody, we know that there is this mode 1, mode 2, some populations, maybe mode 3, so there are at least 3 types of particles in the cloud. But who knows, maybe there are more. And what if this life on Venus, obviously if life on Venus exists, then it is going to be scarce. It's not going to be some jungle-like situation when you have a lot of, life on top of life, like on Earth. Yes, you are going to have essentially a very scarce biosphere because there is very little place for it to exist on. It's just a couple of kilometers of an atmosphere. That's it. I know that there is an entire planet of it, but still, in comparison to Earth, it's very little. And now imagine that if there is certain inhomogeneity of these particles, if you collect them by bulk, yes, you might mix them. And this maybe doesn't even happen naturally in this environment. And the mixing them might change their chemical composition, might change their chemical character in a way that actually destroys the material inside. Or changes it in a way that is no longer recognizable as biological. Now, this is of course very hypothetical and theoretical, but with the sample return like that, or the concepts of atmospheric sample return and cloud sample return that we have to have that also in mind. Now, how do you, so what, suddenly you have to collect individual droplets and prevent their mixing because they do not really mix that much, maybe? Of course, they fuse to a degree, but, to a degree, and collect individual droplets and then analyze them, like to prevent, just in case, prevent their contamination with each other. What if you are actually bringing this back and then you actually expose it to the elements, so to speak, but during the voyage between two planets? How does this affect the sample? You see, with the sample return, with the Venusian sample return, is actually quite. It's much more difficult because the fact that you are actually collecting it changes its character. So there were for example, some ideas that maybe we could use them. What is the aerogels? Yes, aerogels. You can expose the aerogels and the droplets or particles will hit it, and basically you can have some single particle capture thing. But that's why I always put this atmospheric sample return as a last slide, because you see, for other missions, we either have them very well developed and quite advanced, like the Rocket Lab. For the Morningstar missions, the habitability ones, we have a clear view what we would like to do and how to do it, and in what context of the environment on the planet. For the atmospheric sample return, even the engineering and science questions are uncertain. How to do this, and if we go one direction, it will lock us and we will not be and if we decide wrongly, it would have tremendous implications for the entire mission. So yeah, you see, even we are stuck, even at the question, I mean stuck, not stuck. Stuck is the wrong word. There is even uncertainty when it comes to should we collect individual particles or just use the bucket and basically collect everything like whatever, yes? I mean, yeah, I don't know. I have no idea.
I see. So best way would be actually to go there in like some big balloon with laboratory and do the experiment in situ, right? So
yes, like with astronauts or something.
Yeah, of course. Yeah. Oh, of course.
Yeah. This is the sample return mission, which is basically let's build a laboratory, let's build a cloud city first, with actual citizens and then study it. Okay. Yeah, we will go and propose such a project and see how it happens, how it will end up.
Yeah, I mean, you shouldn't have too small tasks, right? You should aim for the most ambitious project. Anyway, if there are no further questions, I think I'll thank you very much again. And I hope you will find time, for example, next year to update us on all of these issues, and you can give.
Oh, absolutely. I mean, some of the issues are probably not going to be updated, like the intricacies of the. Oh yeah. Let me say that. Yes, absolutely, absolutely. I would love to do that. I would love to do that.
Okay. So thank you very much, and good
Thank
luck with your work and missions.
Thank you.
Drsný, já nevěděl, že to testujou i tady. No a proč by ne?